Hello, my name is Allison and I am a biology major from the class of 2019. We will be working through practice problem number 6 from chapter 4.3 in the general chemistry workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you have completed the problem. Then we'll go over it together. Now that you've attempted the problem, let's work through it together to make sure you understand each component involved. First, recognize that the problem describes a reaction of two liquids, hydrazine and dinitrogen tetroxide, and these ignite on contact to form nitrogen gas and water vapor. Like any stoichiometry problem, we should first start out by writing out the equation. So we have hydrazine, which is in its liquid phase, is combined with dinitrogen tetroxide, which is also in its liquid phase. And they're going to react to form nitrogen gas and water vapor. Notice how I wrote nitrogen gas as N2. This is because in nature, nitrogen gas is a diatomic molecule. It's one of the 7 diatomic molecules, which means that for every nitrogen, it's bonded to another nitrogen when it is in the gaseous phase. Now that we have our equation, we should balance it. So since nitrogen is only bonded to itself, we should balance that last. So I'm going to start off with balancing the oxygens. We notice that there's 4 on the left, therefore we're going to need 4 on the right. Let's write a 4 in front of the water vapor. And now that we have 4 oxygens on the right, we can now do hydrogens, which there's 8 on the right and only 2 on the left. So we'll write a 4 in front of hydrazine. And lastly, we'll need to balance out the nitrogens. Well, there's 8 in hydrazine plus 2 in dinitrogen tetroxide, yielding 10. So therefore, we're going to need a 5 in front of the nitrogen gas. Okay, so now that we have our equation properly balanced, we can now begin dimensional analysis. Well, what are we going to start with? Let's look at the problem again. And the only number that we have to start with is 2.5 times 10 to the 24th molecules of hydrazine. Notice that we have excess dinitrogen tetroxide. Well, this means we do not have to worry about a limiting reactant because we already know that we have a lot of dinitrogen tetroxide and only this certain amount of molecules of hydrazine. So let's start off with our 2.5 times 10 to the 24th molecules of hydrazine. Okay. So now we're going to need to get this into moles because we have mole ratios created by the equation we wrote in the beginning. So we're going to do this by converting molecules into moles. And this can be done through the use of Avogadro's number, which is 6.022 times 10 to the 23rd. And this is molecules of hydrazine. And this is into moles of hydrazine. Okay, so now that we have it into moles of hydrazine, we can now convert this into moles of nitrogen gas, since in this problem we are looking for grams of nitrogen gas. Well, looking back to our equation, we notice that for every 4 moles of hydrazine, we have 5 moles of nitrogen gas. Okay, and now we're going to convert moles into grams because that's what our problem is looking for. Well, to do this, we're first going to need to look at the periodic table and find the molar mass of nitrogen gas. Looking at the periodic table, we notice that the molar mass is 14.01 grams per mole of nitrogen. And to convert this into nitrogen gas, since it's diatomic, we'll multiply this by 2 and we'll get 28.02 grams per mole of nitrogen gas. Okay, now we can go back to our original dimensional analysis and we can create another conversion factor. And since we want everything to cancel out, we'll have moles on the bottom and 28.02 grams of nitrogen gas on the top. Okay, so now we should be able to solve our problem. But first, let's make sure that all of our units cancel out. So we have molecules of hydrazine on the top and then molecules of hydrazine on the bottom. moles of hydrogen on the top, moles of hydrogen on the bottom, and moles of nitrogen gas on the top, and moles of nitrogen gas on the bottom. Okay, and that's leaving us with grams of nitrogen gas, which is what we are looking for in the problem. So doing out the math, we should get 145.404 grams of nitrogen gas. However, this is not quite our final answer because we are going to have to factor in significant figures. Well, looking at the problem, we notice that our only source for significant figures is the molecules of hydrazine up here. So therefore, we're going to need 3 significant figures in our final answer. Our conversion factors have no effect on our significant figures. This leaves us with our final answer of 145 grams of nitrogen gas. Hopefully, this video has helped you improve your assessment of stoichiometry problems and has shown you some key skills that are utilized throughout chemistry. Thanks for watching.